Hess's law states that if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process will equal to the sum of the enthalpies of the various steps. Now that is a lot of words for this concept. So if I have these pieces, so I have these equations here, and what I'm looking for is what is the delta H of formation of iron 3 chloride. Let's make that a solid. And I am given these parts here. So iron 3 chloride, we see, is on the product side of this equation, and that's what we're looking for. But it's because it says the delta H F, so of formation, we need the reactants to be simple atoms. FeCl2 is not a simple atom. So this delta H here is not the delta H of formation. So what I need to do is I need to manipulate these equations in order to find a situation where I can add them together and get just the atoms on the reactant side, and then the product be my target product. So if we were to add these together, then what I would have would be all of my reactants over here on the left, and then my products on the right. Now, if I cross out my like terms, reactants and products, I have FeCl2 solid on the product side, and I have one of them, and I have one on the reactant side. So I can cross those out. Then I'm going to combine these, and what I'm left with is solid iron and 3/2 moles of chlorine gas react to form FeCl3 solid. So here we have a formation reaction. This is a synthesis reaction where we have the atoms in their most stable, or in their atomic state or their elemental state, reacting to form a compound. So when we add equations, when we add chemical reactions like that, we're going to add the delta H as well. So again, well, that's a 0. So again, Hess's law, if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process will equal the sum of the enthalpies of the steps. So here are the enthalpies of my steps. Since I've added up the chemicals, I'm going to add up my enthalpies as well. So negative 341.8 kilojoules plus negative 57.7 kilojoules, I get a negative 399.5 kilojoules. So I have chemically added these together, and I have added the enthalpy together. So let's do another one. If we have N2 gas and 2 O2 gas, and they react to form 2 NO2 gas. Now this one's going to be more complicated. So the question is going to be, calculate the delta H of this reaction given these step reactions. So we have nitrogen gas and oxygen gas. Now let's take a look. We're going to analyze this. I need 2 NO2s on the reactant side. I have 1 NO2 over here. Now in order to get 2 NO2s, I'm going to multiply this entire reaction, we'll call that B, by 2. So when I do that, I get 2 NO gas plus, and then 2 times a half is just 1. So O2 gas reacts to form 2 NO2 gas, and what I do to my chemicals then I have to do to my delta H as well. So my delta H, my new delta H is going to be what the original was times the 2 that I just used, and now I have a negative 114.12 kilojoules. So that takes care of my product. Now on my reactant side, I have this 2NO and I need to get rid of it. And I happen to have a 2NO over here, which will cancel it out. So I'm just going to write that one down just as it stands, just as it's written. And that delta H is going to stay what it is. So now I'm going to add this all up. So all of my reactants will be on the left-hand side. And then all of my products will be on the right-hand side. Now I cancel or I cross out the like items. So my 2NO crosses out with 2NO, and I'm going to combine these two. So then my overall reaction becomes N2 gas plus 2O2 gas reacts to form 2NO2 gas. So if you've added your pieces of reactions together properly, you should end up with the target equation. So now I will add up my enthalpies. So I'm going to add this enthalpy because I have to do it adjusted because I did adjust that reaction. So negative 114.12 plus a 180.5 gives me a delta H value of 66.38 kilojoules. Now, because we only go to the 10th place, we really should only go to the 10th place here. So we really should just report 66.4 kilojoules. So we can multiply a reaction through by a factor in order to get our target reaction, but then we also have to multiply the H by that same factor. Now that factor could be a fraction as well. So if we have this problem, and this one's going to be even more involved. So we have this chlorine monofluoride, and it's going to react with fluorine gas to form chlorine trifluoride. What is the delta H? I think I've been leaving off the knots for standard, just for brevity. So this time I'm going to use some different colors in order to try to keep everything separate. If you happen to be colorblind, it may all look the same to you, so I'll do my best to describe. Okay, so when we go to analyze this, we need to look at it in terms of our target equation. So if I start with the target product, and it has ClF3 on the product side, I notice that I have ClF3 over here on the reactant side. Now remember that the delta H, when we calculate it, is going to be the sum of the products minus the sum of the reactants. Now we can flip-flop our products and reactants, and we can write this as 1/2 ClO plus 3/2 OF2, and then put what's currently on the reactant side on the products. But when we do that, we have to change the sign of our delta H. Because what we've done is we keep the same values, but we're flip-flopping these. And because we're flip-flopping these, the sign changes. So now I have my ClF3 on the product side. So that's helpful. So that was the purple equation. Now I need to get F2 over here on the reactant side. So I'm looking and I have F2 here. I should probably change the color of that for clarity. So the F2 is on the wrong side in my first equation. First equation is orange. So I need to multiply that equation through by 1/2 in order to just have one F2. But I also need to flip it around. So if I multiply everything through, so I'm gonna write what I'm doing over here on my delta H. So I'm gonna have it multiplied through by 1/2, but I'm also flipping it around, so I need to change the sign. So I'm going to multiply my H by a -1/2. The negative indicates that I'm flipping it, and the 1/2 indicates the scale factor that I'm using here. So now I need to use this last equation, the middle equation or the green equation here. And I have CLF on the reactant side. CLF is on the reactant side here as well, but I only need one of them. So I also need to multiply this H through by 1/2, but I'm going to keep it in the same order, so I'm going to retain the sign of this delta H. So again, multiplying through by 1/2, I have CLF gas plus O2 gas, but multiplying it through by 1/2. So let's briefly figure out these enthalpies here. So I have a -1/2 times a -49.4. So I have 24.7 kilojoules for this equation. Oop, that didn't make any sense. For this middle equation in this row here. So this was the first equation here. This one goes with this one. So I have 24.7 kilojoules. That's the contribution that this step makes. So with this last step, this green step, I have a 1/2 times 205.6, which is 102.8 kilojoules. And that's the contribution that that step makes. And I just realized I'm a little bit off screen. Let's move this over a little bit. So when we go to add this up, it's going to look a little bit hairy, but just stick with it. So I'm going to write down all of my reactants. And because there's so many of them, what I'm going to do is I'm actually going to write down the products underneath, and that'll make canceling it out a little bit easier. Now I am going to use another color. So basically these are the reactants, and here's my giant arrow. So these are my reactants. I'll just tag that. And then here are my products. So I'm going to look through for my products in order to line up things that are the same. So I have an O2 gas. I have an OF2, so that's over here. I have a Cl2O. I have that here. I have another OF2, so that makes that 3 halves. So I've used that and that. And that, and then I have my ClF3 gas. So now I can cross things out. So my Cl2O, they're the same, so they're going to cross out because they're both on the reactant side and the product side, so they cancel themselves out. I have one whole oxygen because 2 halves make a whole, so that cancels out. And then what I'm left with is F2 gas, chlorine monofluoride gas reacts to form then my product, chlorine trifluoride. And if I scroll back up here, that was my target reaction. This was my target reaction. So now I can calculate that delta H. So I take my negative 266.7 and I'm going, so let me write that out down here. My delta H, 266.7 kilojoules plus 24.7 kilojoules plus 102.8 kilojoules. Add all of those together and I get an overall delta H value of negative 139.2 kilojoules. Another one. Now our target equation for this one is going to be 2 solid aluminum plus 3 chlorine gas reacts to form 2 aluminum chloride solid. So the question is, what is that delta H? Well, if we are given that we have the following reactions, and the phases matter, so don't let go of the phases. So what we have are 4 pieces. We have gaseous hydrochloric acid reacts to form aqueous hydrochloric acid, and that has a delta H naught value of negative 74.8 kilojoules. We have gaseous hydrogen reacts with gaseous chlorine in order to form 2 moles of gaseous hydrochloric acid. That has a delta H naught of negative 185 kilojoules. Then we have aluminum chloride, that's aqueous, reacts to form solid aluminum chloride with a delta H value of positive 323 kilojoules. 2 moles of solid aluminum react with 6 moles of hydrochloric acid to form 2 moles of aluminum chloride aqueous and 3 moles of hydrogen gas. And that has a delta H naught of negative 149 kilojoules. So again, we start with our target. Look at the target. I need solid aluminum chloride on the product side. In all of my reactions, it's this reaction here, the third one, the aluminum chloride aqueous reacting to aluminum chloride solid, that has aluminum chloride on the product side. I need 2 moles of it, so I'm going to multiply this reaction through by 2. I'm going to change my colors. Hopefully that will keep everything organized, or at least a little organized. So if I multiply that reaction through by 2, I end up with 2 moles of aluminum chloride aqueous reacts to form 2 moles of aluminum chloride solid, and that means my delta H will also be multiplied by 2. So I will have a contribution, an energy contribution of this step of 646 kilojoules. Now I also have aluminum metal, so solid aluminum on the reactant side. I need solid aluminum on my reactant side here. I need 2 moles, I have 2 moles. So I'm going to write that step just as it is presented. So 2 moles of solid aluminum reacting with 6 moles of hydrochloric acid, and that's aqueous, react to form 2 moles of aqueous aluminum chloride and 3 moles of hydrogen gas. So because it's just as written, there's nothing I need to do to the H value. I just write it down as it's presented, negative 1049 kilojoules. So I also need 3 moles of chlorine gas on the reactant side. So I'm going to look here. I have chlorine gas on the reactant side in this second equation. It said I needed 3, so I'm going to multiply this reaction through by 3. So 3 moles of hydrogen gas plus 3 moles of chlorine gas react to form 6 moles of gaseous hydrogen chloride. So because I have to change my enthalpy now, I need to multiply it by 3 as well. So that the energy contribution of this step is now a negative 555 kilojoules. Now, I need one more step because I have extra things on here, and it might be easier to see the extra things if we go ahead and combine it now. So I'm just going to draw this part out now. So if I write down all of my reactants, and then all of my products. Remember, the phases are important. Then I cross out what is alike. So on my product side, I have 3 H2 gas. I have 3 H2 gas on my reactant side. I have 2 aluminum chloride aqueous on my reactant side and my product side, so I get to cross those out as well. I also have 6 moles of aqueous. Ooh, no, I don't. I have 6 moles of aqueous hydrochloric acid, but it's a gas on the product side. Let's see if I can move this over just a little bit. So it's a gas on the product side, and because it's a gas, I can't cancel it out. So this is what I'm left with at the moment. I have my 3 chlorine, I have my 2 aluminum, and then I have this hydrochloric acid term that I need to get rid of. Then on the product side, I have my 2 aluminum chloride solid, and I have 6 hydrochloric acid gas that I need to get rid of. So I'm going to scroll back up here, and I happen to have, this is where this term comes into play. So this step here is what's going to help me eliminate those hydrochloric acids. So I have gas on the product side, I need gas on the reactant side, and it is as it's written above. So I need to multiply that equation through by 6. So I'm going to take 6 times this entire equation and add it together. So I have 6 HCl gas and 6 HCl aqueous. And the delta H contribution is going to be 6 times the listed value, which was negative 74.8. So the energy contribution of this step is going to be a negative 448.8 kilojoules. So now when I add this together, my 6 hydrochloric acids will cancel out from both sides, and I should be left with my target equation. So I'm just going to double check that going all the way up. And here is my target equation. This is what I started with. 2 moles of aluminum solid reacts with 3 moles of chlorine gas. That's what I have here. In order to form 2 moles of aluminum chloride solid. That's what I have. So now I'm going to calculate that delta H, and I'm going to add up the energy contributions each step made. So I have 646 plus a negative 1,049 plus a negative 555 plus a negative 448.8. So the overall delta H naught of this reaction is a negative 1,406.8 kilojoules. Because I don't have anything in the tenths place here, I would actually round that up if I were to report that at 1,407 kilojoules. Now, those are rather lengthy and involved pieces. It's a stepwise procedure. You have to go through the chemical steps in order to find that delta H. But we could also ask a question like, calculate the molar enthalpy of formation. Let's move this up just a smidge. So if we calculate the molar enthalpy of formation of NO given 1 mole of nitrogen gas reacts with 2 moles of oxygen gas in order to form 2 moles of nitrogen dioxide gas, and that has a delta H naught of 66.4 kilojoules, and 2 moles of nitrogen oxide gas reacts with 1 mole of oxygen gas in order to form 2 moles of nitrogen dioxide gas. And that has a delta H naught of negative 114.1 kilojoules. Now, I already know that I need nitrogen monoxide in the product. And I'm not real sure what, I know the atoms are nitrogen and oxygen. So although I wasn't given that target equation, you should be able to pick out that this is going to be a combination of nitrogen and oxygen in order to form nitrogen monoxide. Because we are working with an enthalpy of formation, and the definition of enthalpy of formation was the combination of atoms in their most stable or their elemental state in order to form the compound. Now we do need to balance this, and now it's balanced. So we have to derive that target equation, and now it looks like the other problems we were doing. So I know I need this nitrogen monoxide in the product side, and I know I need 2 of them. I have 2 of them here in the reactant side. So if I flip that one around, and the delta H naught value of that is now going to be negative of what I'm given. 2 negatives cancel each other out, make a positive. So I change the sign on my delta H because all I've done is transfer my reactants to products and products to reactants. I've flipped the reaction equation. So now I have my product done, but I need to get rid of this 2NO. So what I'm going to do is just write this equation, the first equation I was given, just as it's written. So N2 gas plus 2O2 gas reacts to form 2NO2 gas. And the delta H naught contribution that step gives is a positive 66.4 kilojoules. So now when I add this together, I keep all of my reactants on the left side of the reaction arrow. And I cancel out what is alike here. So here I have 2NO2 gas on both the product and the reactant side. So they cancel out. I also have an O2 on both sides. So I need to subtract 1 O2 from each side. So now my final reaction is a combination of nitrogen gas, 1 mole of nitrogen gas, reacts to form 2 moles of nitrogen monoxide gas. You see, that was my target equation. So my delta H is then going to be a sum of these 2 parts. So the delta H here is 180.5 kilojoules. But we are not done because the question specifically asked for the molar enthalpy of formation. This is the enthalpy of formation of 2 moles of this compound. We need the enthalpy of formation of 1 mole of this compound. So because this is 180.5 kilojoules for 2 moles of NO, and I know it's 2 moles because of the balanced, the coefficient in front of the compound in my balanced equation, then I can find that the enthalpy of formation of 1 mole of this compound is 90.25 kilojoules per mole of NO.